In this lesson we're going to look at the difference between evaporation and boiling. So boiling is what a liquid does when it reaches the boiling point, but evaporation is something that is happening all the time in a liquid. So we've got a liquid here, and remember that it's represented by a particle model that looks like this. So you've got a whole load of particles that are able to move where they want within the liquid. They're moving with a whole range of speeds and velocities and directions. And as we said in the earlier lesson, they're kind of trapped within a boundary which is known as the surface tension. And we said that that is like a kind of low security prison wall. So the particles aren't able to break through this wall until they have sufficient kinetic energy. So what we need to do is have a look at the distribution of the different energies and velocities of these particles. So we're going to have a look at a graph of this. Again, along the bottom we'll write kinetic energy, and on the vertical axis we'll put the number of particles. And if we look at the distribution of kinetic energies within this liquid, you'll find that there'll be some particles which have low kinetic energy, others which are moving with much more kinetic energy, and we'll have a distribution that maybe looks something like this. Now, as I mentioned earlier, only those particles with enough kinetic energy are able to break through into the gas state. So if we represent that energy here on our graph, supposing this is the kinetic energy required for the particles to evaporate, let's say to go from the liquid into the gas state, then on our distribution only these particles here have enough kinetic energy to escape into the gas state or evaporate. So let's say that this liquid is water, for example, and at the moment it's at a temperature of room temperature, say 20 degrees Celsius. So the temperature of a substance is really a measure of the average kinetic energy of its particles. So that you can see that looking at this distribution, the average kinetic energy of the particles is going to be somewhere around about here. So the average kinetic energy is a measure of the temperature of the liquid. So although the temperature of the water, which is 20 degrees Celsius, is still quite a long way below the boiling point, there are still water particles present with enough kinetic energy to escape into the gas state. Right, so what's going to happen is that these particles are going to escape even though we're not at the boiling point, so evaporation will occur. Now when these particles escape, what happens is the average kinetic energy of the particles in the liquid decreases a little bit as a result of these very high energy particles escaping. That makes sense. So what happens to the liquid when water particles start to evaporate is that the temperature of the liquid drops down a little bit. But if the temperature of the liquid drops down a little bit, what happens then is that the liquid, the water, is now at a lower temperature than the surroundings. Yeah? Okay, so as a result, heat will start to flow from the surroundings back into the liquid or the water until the temperature of the liquid is the same as the surrounding temperature. In other words, this distribution will re-establish itself again. So we'll get some more particles now at this top end of the distribution with enough energy to escape from the liquid state. And so these will escape again, causing the average temperature of the liquid to drop. More heat will go in to the liquid, to the water, to reach thermal equilibrium, and so on, and the process will continue until eventually all of the water has evaporated. So this water will eventually evaporate, even though it takes 2 or 3 weeks to do so. Now we can appreciate in a more dramatic way what's going on here by doing this. If you take your hand and pour some ethanol in your palm, okay, there we go. Ethanol is a more volatile liquid than water, and so evaporates a lot more quicker. However, its boiling point is still 78 degrees Celsius. So so it'll evaporate even though the temperature isn't at the boiling point. Now, just as we've said here, within this liquid structure, some of the particles of ethanol will be moving very quickly indeed. They'll have enough energy to move into the gas state, and as they do so, the average kinetic energy of the particles drops. Therefore, the temperature of this little pool of ethanol will drop down, and therefore heat will pass into the ethanol to increase its temperature. Now, in this case, where is the heat going to come from? Well, it's going to come from your hand. So as the ethanol is evaporating into the gas state, you will immediately note that your hand starts to get cold, because it's drawing heat energy from your hand, really, in order for those ethanol particles to evaporate. So we can say that heat energy is removed from your hand to help the particles evaporate. In fact, exactly the same thing happens when we sweat. The body wants to maintain its temperature at 37 degrees Celsius. Now, if you're running, what that means is your metabolism is working harder, so your body temperature increases. Now, your body doesn't want that temperature to increase, so what it does is it starts to sweat. And when it sweats, what happens next is the water on your skin evaporates, and as it does so, heat is taken from your body to help those water particles evaporate, and therefore your body cools down, in the same way as when the ethanol on your hand evaporates here in this situation. So we've just looked at what happens when liquids evaporate. In the next lesson, we're going to have a look and see what happens when liquids boil. We're going to have a look at boiling.